Okay, so what's a binary mixture? Remember when we first talked about mixtures? They were the components of a mixture are physically and chemically distinct. That is, they don't react with one another. They can be separated by physical means. Okay, so we're going to use that fact to separate this mixture. This mixture, I can tell you, is sand and table salt in a certain ratio that you don't know yet. You have to figure that out. Okay, so in most labs, exercises, actually research too, you try to simplify your objective down to the easiest, simplest concept possible. What we're trying to do is to separate these two. Okay, so how are we going to do it? Well, is sand soluble in water? Nope. So just find out what's the mass of this. Right, you need to know that mass. And then dissolve it in water. Right? So when you mix water into your sample, it's going to dissolve that, but not that. So now how do you get them separated? Pass them through a filter. Right? Pass it through a filter. And what do you get on this side? So there's your filter. On this side, you get aqueous sodium chloride. On this side, you get sand. Okay, now they're separated. But in order to find out the composition of the original, they need to be dry. Okay, so how do you dry this one? Right. Just put it on a hot plate in its beaker and dry it down until the water's gone. And you got nothing left but sodium chloride. So how do you know what's in your beaker is sodium chloride? I mean, how do you get at the mass of what's in your beaker? You have to know the mass of the beaker beforehand. You got to weigh that beaker first. Then when you filter the solution into the beaker and dry it down, you know that when you weigh it again, the difference is due to the sodium chloride. That gives you the mass of the sodium chloride. Okay, so you got the mass of the sodium chloride, you got the total mass. You just need one other. You need to know the mass of the sand. Right? So how do you do that? Well, it's going to be on that filter. It's kind of hard to get it out of the filter. So you need to know the mass of the filter beforehand. And in fact, I think the method tells you to weigh the filter and the watch glass. There's a watch glass that the filter lays on. Okay, so you know the filter paper and the watch glass mass. Then when you filter it, you put the filter paper back on the watch glass, the same one you weighed. And then you need to evaporate the water from the sand. So how do you do that? Well, you take this over here to another hot plate, and you have a boiling water bath that makes steam. And you put your watch glass with the filter paper and the sand on it. And the heat from underneath, there'll be enough space for the steam to escape out from the sides. So it won't just continuously wet your paper. It'll just deliver heat. And as you heat it, then you're going to drive off all the water. And once that's done, then you take the watch glass, the filter paper, and the sand, all those three together, weigh them again. You've already got the weight of the watch glass and the paper because you did that beforehand. Now the difference is the sand mass. Now you have the mass of the sand. You have the mass of the sodium chloride. You have the total mass, and you can calculate a percent composition. Okay, that's the whole lab right there. Now the trick is how to get there, because there are certain techniques that work better than others. Let's see. Pre-lab questions. Maybe the pre-lab questions will address some of those issues. Pre-lab questions. All right, first, read an authoritative source for a discussion of filtration. Okay, well, since I didn't give you the method last week, you won't have that available. And there are no points assigned to it anyway. So what does filtration do? What's the principle behind filtration? Particle size. You can have various size filters. In other words, when I say size filters, I mean pore size. How big is the opening that stuff goes through? If the pore size is very big, then you can only catch big stuff. But if it's small enough, you can catch any solids that are suspended in our case, water. And then the water or the solution goes straight on through and leaves the filtrate behind. Okay, that's the principle of filtration. What safety precautions should be taken when evaporating the filtrate containing sodium chloride? Okay, the filtrate containing sodium chloride is that one that's in the beaker in solution, and you're going to evaporate it on hot plate. Well, the method tells you to evaporate it slowly. But the real key is you can evaporate it pretty fast in the beginning. But as you get down to a very little bit of water, you're going to develop hot spots in that salt matrix where you still got some moisture. And those hot spots are going to cause the remaining water to go pew, 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 sputter. And what that'll do is take your sample and go throw it out on the floor. And so at the very end, as you're heating the solution, slow down the rate, cool down the plate some at the end. And you just have to, that's a judgment call. How much do you cool it? Okay, other safety precautions. Well, you got a steam bath. That's what we call it. That beaker with the boiling water in it is our steam bath. So the watch glass on top with, now we're talking about the sand and the paper in the watch glass. That steam bath is producing steam and it will burn, right? If you get too close for too long, it will burn you. So avoid contact with the steam. That means you're going to need PPE, personal protective equipment, gloves, and eye protection. If you left your eye protection somewhere else besides here, I've got some more safety glasses up here. Anybody think of any others? Well, you got hot surfaces, right? Hot plate, you don't want to touch those. I've done it before. It hurts. Okay, define the following terms as they apply to this experiment. Homogeneous mixture. Well, what's a homogeneous mixture? It's a solution. In other words, it's the same composition throughout. So which one of these is a homogeneous mixture of all the things that you're going to look at during this experiment. The salt solution, that's a homogeneous mixture. How do you define evaporation? It's not a trick question. What happens when you evaporate something? You change phases, right? You go from a liquid to a gas, right? So we're going to evaporate water from liquid to gas. That's how we remove it from our samples. What's a residue? Well, we actually will have two residues. Suppose we've got the salt water that we're evaporating the water from. The residue is the salt that's left behind after we evaporate the water. The other one is a suspension of water and sand. The residue for that one is what's left in the filter. Oh, we got a lot of questions, don't we? This is eating up a lot of your time too. And it takes a long time to evaporate this stuff. So let's get a move on. A student is asked to determine the percentage of each component in a mixture of sodium nitrate and calcium carbonate. The mass of the sample used was 2.21 grams. So the mixture is 2.21 grams. All right. The student extracted sodium nitrate from the mixture with water and separated the insoluble calcium carbonate by filtration. Okay. So the sodium nitrate is in solution, and the calcium carbonate is in the filtrate. So this will be comparable to our sodium chloride, and this will be comparable to our sand caught in the filter. After evaporating the filtrate, the student recovered and dried the sodium nitrate, okay, and found that it weighed 0.43 grams. That's after we subtracted out the container. That's what's left over. That's the net for sodium nitrate. The student dried the insoluble residue of calcium carbonate, found that it weighed 1.67 grams. Okay. Now for the questions. What's the percent sodium nitrate? It's this divided by the total, right? What's the percent of calcium carbonate? It's this divided by the total times 100. Okay? Calculate the total mass of sodium nitrate and calcium carbonate recovered. Now we add this one together with this one. Right? And that's how much was recovered. Should it be exactly that value? Only if you're really, really, really good at it. More than likely, it'll be less than that value. And just looking at those numbers, yeah, it looks like it's going to be less. 2.10. Okay. So what's the percent recovery? This one divided by that one. That's the percent recovery. This is how much you recovered. That's how much you started with. So the percent recovery is that ratio. So what's the percent error? This is the one that might give you trouble. What's the percent error? You were expecting that one, and you got this one. So the percent error is 2.10 minus 2.21 divided by what you expected times 100. That's the percent error. And sometimes we express percent error with signs, positive or negative. If you write it this way, then that says it's a negative sign, right? This negative is bigger than that positive. The negative sign says that we recovered less than we started with. The negative sign tells you. But sometimes statisticians don't care about the signs. So you could just take the absolute value. And that would be valid too. So the percent error is such and such percent. Okay? That's all the pre-lab questions.